Alright, I have more people in here now. So let me do this. I think it's a really good game. I've never actually finished it, but that's probably because I would get distracted by other games, because it's quite long. So, like, the premise of the game is that you are a person that is working a 9 to 5 job for some corporation, and like you hate it, and then your grandfather dies and leaves you his farm, and so you go to the farm, and the whole point of the game is to, in 2 years of 4 seasons per year, and each season is 30 days long, I think, do as much as you can to change your life. And not just yours, but the life of everybody around you. And so you can befriend everybody by giving them stuff. You can fix up the town's community center, and so that the town can come back together and be like a town again. You can get a boyfriend / girlfriend, have a family. You can build things on your farm, like make a bigger house, build a barn, have cattle. You can name the cattle. You get a cat or a dog. You get to pick one. My cat would always run around outside in the rain, and I don't understand like why she would do that, but yeah. No, it's a really good game. There's even parts of it where like you run around in a mine shaft to like find cool stuff so you can make better tools out of it. But there are monsters there, so you have to defend yourself, and you can actually die in the game. And if you die, then you just kind of wake up back at your farm and lose all of the stuff that was on your person. Don't do that. That turns out to be really bad, losing half of your shit in your inventory. But I really enjoyed it. I just find it really stressful because there's a timer at the top in the corner of the screen, and it just keeps going. Like, nothing stops it other than conversations. And if you're playing multiplayer, nothing stops it at all. So, I was playing multiplayer with another chemistry faculty member, and I got caught in a cutscene at like 11 p.m. at night, and the time just kept going, and by the time I got kicked out of the cutscene, my character passed out because it was like 2 a.m. Is lab worth half your grade? No, it should be like 20%, I think. It's in the syllabus. Check the percentages in the syllabus. Like, all the points all the points are shown in the syllabus. Oh yeah, you can open the menu in single player. That'll change it too. We were talking about how conspiracy theorists thinking that cell phones cause ionizing radiation are just a bunch of whack jobs yesterday, because the dangerous types of light are over here. So this region and further. These are the ionizing radiation. When I say ionizing, what I mean is that this can take something and remove electrons from it. And that's going to be very relevant to us later, because kind of the whole point of Chapter 3 is to figure out what are the things that we can do with electrons and light. And one of those things is ionize electrons. And so we're going to learn all about ionization energy. How easy or hard is it to ionize different elements? And that will correspond to how easy or difficult it is to do chemistry with them. So that's really cool. All right. Yesterday I gave you this formula. I'm going to write it at the top here. C equals lambda nu, where lambda was the wavelength and nu was the frequency. So we're going to do this practice problem together. A blue laser has a wavelength of 410 nanometers. What is its frequency? Just so you get a feel of what these numbers that we're going to be working with look like, because they are very weird. Oops, that won't work. There we go. All right, so let's write the equation again. And I want to solve for frequency, so that's this. So I'm going to rearrange my equation. So frequency is speed of light divided by lambda. And I know that the speed of light is a constant, which you can just look up in the slides, or it's on Google. Google will give you the speed of light to a bunch of numbers. However, we are going to just use 3 sig figs for our purposes. That'll be fine. So I have to enter all of my information in units that are going to cancel out. So if the speed of light is in meters per second, and lambda is in a length, I'm going to need to put lambda in meters. So 410 nanometers is the same as me saying this, right? Or I could do this. Well, actually, I don't get to keep the 0. Either of these is fine, but if you're just punching it in your calculator, anytime you see nano, you could just stick 10 to the minus 9. This isn't proper scientific notation, but your calculator doesn't care about proper, right? So just type that in your calculator. That should be a times there and there. And so now just punch in the calculator. And you should get a ginormous number. 7.3 times 10 to the 14? And I gotta worry about my units here. So meters divided by meters cancel out. And I have 1 divided by seconds. So my answer is going to be per second. Another way of writing this, so that we aren't just dealing with weird fractions, is to write this. So you might see that come up a lot, where you see something raised to the negative 1 power. That's the same as me writing something over that. So frequencies for light tend to be extremely high. So a wave of light will oscillate on the order of 7 times 10 to the 14 times per second. That's a lot of times. And that's actually pretty typical. All right, so that's a very simple example. Let's have you try some of these examples that are using the same sort of gimmick. So if you look at your microwave on the label on the back, it should tell you what the frequency of the wave is. I thought it was 2.54. Maybe it's 2.45. I don't know. Anyway. So using the frequency of a microwave, which is 2.450 gigahertz, according to this problem, tell me what the wavelength is of a microwave. I wonder what it could be. Microwave? So there's your hint what your wavelength should be, right? For problem number 2, the color of a star dictates its temperature, because the hotter something is, the more blue it ends up being, because blue photons have more energy and are more intense than red photons, because we know by their frequency. So our sun is sort of in the middle. It has a peak wavelength of 500 nanometers. So tell me what color that is. You'll have to go back to the visual slide to do that, or you could just look outside. Oh wait, we live in Seattle and it's nighttime. And then tell me what its frequency is for that photon. And then the last one's kind of a challenge problem. What is the radius of the Earth in meters if it takes light 1/7 of a second to circle the Earth? Now, that's 1 sig fig, so assume 1 second is, or 1/7 of a second is exact, so that you can get a more reasonable number. To calculate the radius of the Earth, you will need the formula for a circle. And so, so circumference of a circle is 2 pi r. So you'll need that. Go ahead and try these 3 problems, and we'll go over the answers in just a second. A few more minutes, and we'll go over the answers. Post any answers you get in the chat here, and we'll compare them. All right, let's go over the answer here, and then we'll see if I can address any specific questions that people might have. All right, so I gave you a frequency. And, oops, excuse me. I didn't hit mute there. I apologize for that. I gave you a frequency, and we want to find the wavelength. So the formula that we have is C equals lambda times nu. So I'm going to rearrange this so that we get... Oops, that's not what I want. I want to find the wavelength here, so that's going to be C over nu. And we know that the speed of light is always going to be this constant. So let's punch in all the numbers here. So I've got the speed of light. And then I've got the frequency, which is 2.450. Giga means 10 to the 9. Hertz means per second. So these per seconds will cancel out. And we're going to get a number that's pretty small. 3E8, 2.450 times 10 to the 9, 0.122. Look at me trying to mislead you with microwaves being in the micrometer region. Some of them are, but some of them aren't. The microwave region is actually pretty broad. If we go back to, let's see here. If I go back here, you'll see that, oops, that's the wrong screen. The region where we have microwave is actually just kind of like this region right here. And so you can get wavelength that's around 10 to the minus 1. In fact, the micro region is actually over here. It's in the infrared. I don't need to erase this. We're not coming back to this slide. So, All right, let's look at number 2. Oh, we are coming back to that slide. So if you look at 500 nanometers, you should have gotten yellow, or yellow-green is the answer for that. That's about the color of the sun. I think specifically the most prominent color is yellow-green for the sun. And the reason that I know that is because tennis balls are made to be a specific color that is considered the easiest color for our eyes to see because a tennis ball is flying at you really fast. And that yellow-green color is the highest wavelength that is principally emitted by the sun, and our eyes have evolved to see that wavelength the best. And it happens to be around 500 nanometers. So let's figure out what the frequency is. I'm hitting all the wrong buttons here. I started drawing on the other slide. So if I want to solve for the frequency, I'll just rearrange the equation. C over lambda. I don't know what happened there. Three times 78 meters per second. The wavelength is 500 nanometers, which I'm going to write as 500 times 10 to the minus 9 meters. And those meters will cancel out, and I will get, looks like 6 times 10 to the 16 or something. 3e8, 5e9. Oops. That's wrong. Hold on. 5e negative 9. There we go. Yeah, 6e16. Oh, the other thing that you could be writing for these is you could just do this. You could just write hertz, right? There you go. All right, for the last question, we're being asked how thick is the Earth? Is it dummy thick? Who knows? Well, we'll know in a second here. So, if I draw the Earth, here's the Earth, and light goes around it. And we'll assume that it's just it. I knew somebody was going to comment on that. We'll assume that our beam of light is going like right across the surface along the equator. So it's not going around like at the satellite level, although that wouldn't really affect the radius that much because the Earth is much, much, much larger than we give it credit for. So it takes light 1/7 of a second. We're going to assume that it's exact for this, just so that we don't end up with 1 sig fig. You got 6 times 10 to the 14 for the top one. Make sure that you are punching the number in. It's 500 times 10 to the minus 9 and not just 5 times 10 to the minus 9. The other thing that you might need to do is use parentheses around the number at the bottom. Wait a second, hold on. I didn't do 500. I did 5 times 10 to the minus 9. Okay, so hold on. Because I was doing that in my head, and I was like, wait a second. 8 minus 9 is, or 8 minus negative 9 is 17, but then I go 16, 15, 14. 500 E minus 9. Yeah, now I got 6 times 10 to the 14. Okay. Yeah, I had a mistake. Thank you. Whoops. There you go. Let me circle that just so anybody going fast through the video and then tabbing forward. So correction. There we go. Now I can go back to talking about how dummy thick the Earth is. All right. So if our light goes around this far and it takes 1/7 of a second, then if the speed of light is 3 times 10 to the 8, man, I am not good at writing zeros today. I'm going to write it like this time, because then I can say 1/7 of a second and just cancel these out. We can find out what the circumference of the Earth is based on this amount of time. So 3 times 10 to the 8. No, I just forgot to write those zeros in there. Times 1/7, and I get 1, 2, 3, 4. So 3, 4, 5, 6, 7. I'm just going to do 3 sig figs. That'll be good enough. 3, 6, 7. Yeah, that's good. So that must be the circumference. So what that means is if this is the path that light is traveling, then that's going to be equal to 2 pi times the radius, which I can then solve for. And so this will be the radius of the Earth in meters divided by parentheses 2 pi. And I get 6820926, so 6.82 times 10 to the 36. So this many meters, which would be the same as me writing this. Now, I know the problem asks you for the circumference in meters, so the top number would be fine. But the reason I'm giving you the bottom number is because if we can go to the internet, we type in radius of Earth, the number that it gives me, oh, that's miles. I had it in kilometers, in kilometers. There we go. So I got 6820 with 1 sig fig or so. I made it 3 sig figs, but there's definitely error there. And if I go to Google, here's the number it gives me. That's not a number at all. In fact, that's nothing. There it is. So obviously we have a lot of error because we only have 1 sig fig. But we got the first number right, 6. Like, that's pretty good, right? So we were within an order of magnitude of the correct answer. Note, the Earth is not quite, but almost a perfect sphere. The Earth is only very slightly flattened. Imagine the universe. All right, we'll imagine that later. All right, so those are some very simple problems that you can do with light. We're going to dig into some more complex problems as we go on with the lecture. All right. This next bit is very conceptual. We're going to talk about other properties of waves, because these properties are going to correspond directly to electrons in a very weird way. So the first thing we're going to talk about is a standing wave. A standing wave is a wave that is constrained to some physical location between a boundary. So for instance, if you were holding onto a rope at both ends, like the little dots on the end were like people's hands, and those hands were staying there in space. And then you applied energy to the rope, Like maybe cause it to spin, or like if you've done jump rope where one person holds one end and the other person holds the other, and then you swing it around, that would be an example of a wave. Now, you could also hold with your hand, like if you held the rope here, so this is my thumb and my fingers holding onto the rope. And if you kind of shake it up and down at the right frequency, what you'll end up getting is just this wave that goes up and down. Now, if you do it at the wrong frequency, you just kind of make a mess, right? It'll just sort of waggle all over. But if you do it just right, you can make it consistently go up and down. And I'm actually going to show you a video of that in a second here. Now, if you do this at a faster energy, then you could actually make it do that in 2 places, or 3 places, or 4 places. I just read your wide at the waist comment, and I was like, huh? And I realized you're talking about Earth. I'm not sure if I can or need to elaborate on that, but anyway, let me know. Now, the amount of energy that is required to do these transitions is very specific. And what I'm going to show you on this next slide here, let me do this real quick, is that it's easy to make no standing wave and just get a mess, but it's pretty fine amount of control is required to get a standing wave to stay there. So that's way too zoomed in, so hold on. All right, so we're going to do, this guy's going to do a standing wave, and I'll actually turn on the audio for this because it's probably not going to get copyright struck.
For this demonstration, I have my able assistant, Parker. Parker, smile at your admiring audience. And we will be demonstrating transverse standing waves. I'll also demonstrate traveling transverse waves. Here's a traveling wave. I'm starting the wave by creating a disturbance here with my hand that is perpendicular to the direction of propagation of the wave. So I'll move my hand up and down, and you'll see that the little bump in the spring travels from me to Parker and then back to me again. And you'll notice that when the wave hits Parker's hands, because he's holding it firmly, what was a peak heading toward him converts itself into a valley as it bounces off of his hands. So then a standing wave is where you pick a frequency that matches the length of the string in such a way that the waves created from my side of the string and bouncing off of Parker's coincide with each other and reinforce each other to create a standing wave pattern. The lowest frequency standing wave pattern is this one. It's called mode, M-O-D-E 1, or the first harmonic, or in other words, also called the fundamental mode. So
I'm going to hit pause there, and we're going to go talk about our waves just a little bit. So you can see how these waves are made, like no big deal. Now, in a second, he's going to do this again, but he's going to apply a different amount of energy to try and get this second wave right here. And when you do that, you get this region in the middle that doesn't really move. Yeah, waves are kinetic energy. Light, however, is not kinetic energy, because kinetic energy requires a mass component as well as a velocity. And light essentially has zero mass for our purposes, because it's not matter. So these spaces that form when we get these waves that reinforce each other just right don't move at all, and these are called nodes. A node is a region where, given the amount of energy that is put in to make this wave exist, the amount of energy that would be required to make the node move at all is infinite. The node doesn't move for any reason, because the wave function, we'll call it, the equation of this wave, this hump moving in this direction and then this valley moving in this direction, are at the exact same frequency, right? When we had the longitudinal wave that was moving back and forth, if you keep making waves at just the right frequency and speed, they'll exactly cancel each other every single time at the node. And so that node forms when this specific amount of energy is put in there. If you put in a different amount of energy and you, like, say, something between these two, what you end up getting is a mess and you don't see the waves. They just bounce back and forth forever. But there are specific frequencies, these are the harmonics that he's going to talk about, that when you line them up, you can get multiple standing waves. So this would be the first standing wave, this would be the second one, and this would be the third one. And between each wave is going to be a node. So let's see if he can do that. He actually can get this to work with the second one. And then the third one, it starts to work for just a second. So I'm going to have to pause the video and try and catch it. But we'll see this in action here.
Lowest frequency mode that you can get in a transverse standing wave. If I double the frequency of that mode, I get the second harmonic, or second mode, and sometimes called the first overtone.
Oh, damn it. I tried to pause it so that you could see the wave. So hold on. There we go. Just in case you didn't know this, on YouTube, if you want to go one frame forward or back, comma or period. So comma will let you go back one frame, and period will let you go forward one frame. Super useful for teaching. These are the things YouTube doesn't tell you. So you can see right here that if you look right here in the middle, this is my node. And so the spring at that location doesn't move.
And this one, if you'll notice,
relatively
is
speaking,
going twice as fast as the fundamental mode. It has a node that's exactly halfway between Parker and me. And that's a node where there's approximately no motion going on. 2, 1, 2. So now I'm going to try and triple the frequency and get a standing wave pattern that coincides with the third harmonic or second overtone.
And I'm going to have to pause it, like, in a very specific spot here, because he gets it for, like, half a second. I think he tries it again.
Let me try again.
Oh, I saw it. There we go. So you can see that here's the node, and here's the node for these waves. There it is. You can kind of see it.
Okay, I think I've got it approximately now.
Yeah, there it goes.
I think I had it for a little while there. That's the third mode, where the...
So you can make these waves by imparting a frequency, which is going to correspond to an energy, and we'll talk about that energy later. How many of these waves are possible? Well, theoretically, you should be able to do this an infinite number of times, right? So if I have some amount of energy, I'm going to say some amount of energy corresponding to 1 or 2 or 3 or 4, I could do this all the way up to n equals infinity, where I have an infinite number of waves that stand. And so I'd also have an infinite number of nodes minus 1, because there's always one fewer node than whatever number you're on. So for the number of half waves that you observe, there are going to be n minus 1 nodes. That's going to be important. Now, because this only works for given energy, so these highlighted energies that I'm showing, like going down is increasing energy, but I can't do a frequency, like if this was like 10 hertz and this was 20 hertz, I could not make this happen at 15 hertz. Because I would just make a mess. Like I'd get 1.5 standing waves and they would just sum together in a weird way and it wouldn't work. So only certain energy levels work. And this is called quantization. Quantization means that you need a certain amount of energy to make it to work. If you use a different amount of energy that isn't one of the quanta, you don't get a result that happens. You just get garbo. I didn't realize I'd actually written the ends there already. Now, this is a one-dimensional wave. What if we did this in 2 dimensions? Well, let's see. You can already hear the funky music that will happen in this one. I like this video just because it has good music, but what we're going to do here, to explain this plate, this right here, you can't see my cursor, there we go. This right here, this is a frequency plate, and it's hooked up to this, sorry, it's a frequency generator. It's hooked up to a plate that will oscillate at the frequency that is programmed in there. And we're going to throw really cool sand on it and have a rave, basically. So here the sand is just scattered about randomly. We're going to put it at a specific frequency that creates a standing wave. I'm going to hit pause before we go through this. But what is the sand doing? The sand is bouncing on this plate because the plate is vibrating at a specific frequency. But that vibration can be... Oops, sorry, I changed to this. That frequency can be explored as a wave. So this is what the plate is doing. And so if the plate is going up and down, this is the center line, we'll say, where is the sand going to go? It's going to try and connect or collect in the locations that don't move, because when the wave changes, now it's going to be like this, right? So the sand is going to try and go in the nodes. So what you are seeing in the 2D waves are the positions of all the nodes. So I'll go back to this and let it play through a little bit more. And you can see down here where there's a frequency. These frequencies correspond to a certain amount of energy. The higher the frequency, the more energy you have to put in to get this. I'm actually waiting for a specific one here. I might not actually get to see it, so I'm just going to pause it right there. So you'll notice that in 2 dimensions, nodes are kind of weirdly shaped. Like in one dimension, they were just like points along the line that occurred. But in 2 dimensions, they're like lines and stuff. And there's 2 different types of nodes that we care about. One node that I want you to look at is going to be called a radial node. A radial node means a node that is some distance from the radius. So, for example, if you were this far away from the nucleus, say the nucleus being right here, then a node forms. So that exists up here also, and also up here, and also down here. That would be a radial node. You're at some radius away from the nucleus. A better example might be over here. So here, if you were this far away from the nucleus, you're a node. The next one would be called an angular node, which would just be at some angle along the nucleus, you're a node. There really isn't a good one here, but we'll try and find one. So that's pretty cool. I actually have a picture of a radial node on the next slide, so we'll just talk about it there. So here you can see, now that I can draw on it, I can't draw on YouTube. So here are my radial nodes. At a certain distance, the sand gathers because that part of the plate isn't vibrating. That's the node. In different frequencies, my node is angular. I forgot the word there for a second. So this is a radial node. And this is an angular node. I should just let my slides do the talking for me. Like, I don't know why I'm labeling them myself. All right. So these are just 2 different ways that nodes manifest themselves in 2 dimensions. Now, we're going to be working in 3 dimensions. So instead of having like a circle within this area be our node, in our radial node for a 3-dimensional representation, it would end up being like a sphere. So in 3D, this would be a sphere. And for an angular node, instead of it being a line in 3D, it would be a plane. Now, why am I going to all this trouble to discuss waves? Remember when I said earlier, electrons behave like waves, which means that the electron cloud is a wave. And unlike sand gathering at the nodes here, electrons are the wave. And so we will find electrons everywhere but the node. So understanding why waves do what they do, and then visualizing that is going to help us a lot when we get to visualizing this in 3D with electrons, because electrons are essentially the inverse of what you're seeing here. On this plate right here, my electrons would be the black background, and the sand would be the nodes. You would never find an electron in any region that has sand on it, because the electrons can't be there. They're the waves, so they can't exist at the node. How do angular waves form? It's just a function of frequency. Excuse me. So, as the plate vibrates, you end up getting places radially where the energy cancels and sums to 0. But at specific frequencies, you don't just vibrate radially, you start vibrating in all directions. And so, like, my wave could be, oops, sorry. My wave could be going back and forth and back and forth and back and forth. But also like this, and it does that at other places too. And so this vibration and this vibration might cancel out in all along this axis, and you would just get a line. That's my best explanation. But yeah, these are two-dimensional S and P orbitals. That's exactly what's happening here. So the short version of how do you get this is sort of just, this is just mathematically what we observe. And I'm sure that there's an equation for it, but it's really complicated, and I don't actually know it off the top of my head. All right. So we're going to come back to this information again later on, but knowing how this behaves is going to be really helpful to developing our understanding of, oh, this is why these shapes are like this. Kind of like how Michael is mentioning in the chat. You're going to see these orbitals in 3D, and this is how they're made. It's just instead of me hooking a plate up to a vibrating energy generator or function generator or whatever we want to call this, the electrons do this from ambient energy around them, such as their kinetic energy, their momentum, and then other energy that we impart it through light and heat and stuff like that. All right. This is a totally different subject, but we're just going to bring it up because there's some useful information in here. Any object that is sufficiently hot enough emits light, and this is called the Blackbody effect. Blackbody radiation occurs depending on the temperature of the object, and the hotter it is, the higher the average energy of wavelength is that comes out of that. Now, if you have any random blackbody, such as, say, the sun, it will emit a range of frequencies and wavelengths. And so this is called a continuous spectrum. So, for example, if you look at the sun, it will emit every color of light through this range, and it even keeps going on both directions. The highest amount of light is right here. This is the peak for the sun, is that point right there, which corresponds to yellow or yellowish green. That's why you see yellow when you look at the sun in like a picture, or like a photograph from outer space. It looks yellow-orange. The actual highest wavelength that comes out is slightly in the green region, interestingly enough. So, cool. Black bodies make continuous spectra. There's an issue, though. We'll get to that issue in a second. So here is the yellow line that you see behind my this blue line is my theoretical curve. There we go. And then this right here is the actual model of the sun. And so you can see that our theoretical curve matches up pretty well with what the sun emits. And so since this equation has some formula that has temperature in it, we can use it to conclude what the temperature of the sun is at the surface. So it's about 5,250 degrees Celsius. It's pretty hot. Now, this emission curve peaks right here. This is our yellow-green light. But it extends in all directions, and so the sun is, in theory, emitting all sorts of different wavelengths of light that we can detect. But sometimes when we observe bodies, we notice that there are some spectra that have holes in them. I don't know why the photoelectric effect is next. I don't want to talk about this yet. We'll get back to the photoelectric effect. And so these spectra are just absent from specific bodies. For example, if you look at the sun A common thing that you will see that is absent is you will see that there are 2 purple lines missing on the sun spectra, a cyan line and then a red line. Oh, there they are right there. They're these lines right here. And so this is particularly prominent if you look somewhere like around the corona of the sun. I know I shouldn't say the word corona, but the corona is just the outside of the sun. And you'll see that these lines end up missing from the continuous spectrum. Here they are down here just by themselves. What ends up happening is that the light that is emitted by the sun in every frequency, specifically these wavelengths, get absorbed by something. And they give us what's called a line spectrum. So a line spectrum only has certain wavelengths present, as opposed to all of them. Why the heck would all of the lines be present in a black body, but only some of them be present in just a regular element by itself? That's interesting. In fact, a lot of people tried to figure this out. Why the heck are only certain lines visible in elements by themselves? But if I look at a black body, which presumably just has all sorts of crazy shit going on in there, there's every color. What could be causing that? And that's going to be the whole premise behind quantum mechanics. So when we come back, we're not going to go to the Bohr model just yet, because I got to talk about the photoelectric effect. But when we come back over the break, try and think of like what the heck would cause certain elements to emit only specific frequencies of light as opposed to every frequency of light. And I'm sure that you probably have no idea, but think back about what waves do and where nodes are and how we were able to get different nodes and different waves. And you might actually kind of get close to the answer, believe it or not. So think about that just a little bit. That's not the break timer. We'll start the timer. I'll put more whatever this is on Stardew Valley. And we'll reconvene in 10 minutes. I'll see you then. Wow, 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 wow. Oh. So close, and yet so far. We're going to go back a few slides so I can talk about the photoelectric effect. So, the photoelectric effect is the last sort of property of light that we're going to ascribe for now before we do a discussion of actual atoms and try and figure out what is light doing, why does it do all of these crazy odd things. Maybe this has something to do with electrons. So, the first phenomenon that we want to mention regarding the photoelectric effect is that which was observed by Einstein. So Albert Einstein, you've heard his name, I'm sure, was the first to observe the photoelectric effect in specific metals when specific light was shined upon them. And so the summary of the effect is that light hits the surface, and when the light hits the surface, electrons get expelled from that surface. In fact, those electrons can be used to pass through a circuit and then through a voltmeter and then back to the plate. You can make a circuit out of this. This could be used to power things. And in fact, it is. It's called solar power. In solar power, the photoelectric effect knocks electrons off. They hit a terminal and they run into a battery where we charge the battery. And then the electrons go back to the surface of the metal that they were once on. They complete the circuit. Now, Einstein noticed some particularly interesting things about the photoelectric effect, and we're going to go to this to talk about them. So, Einstein did a bunch of experiments with the photoelectric effect, and here's what he discovered. So first, Einstein tried photons that had high amplitude and high frequency. So, for example, that would be something like this. And he shot them at a wall to see if the photoelectric effect was observed. And it was. So the next thing he did was he tried turning down the amplitude. Use fewer lights. But the lights that are used will still have the same high frequency. Will this affect the photoelectric effect? And the answer that he observed was no. It was exactly the same as the previous experiment. Okay, well, let's try the other condition where I have a high amplitude but a low frequency. And so that would be something like this. And what he noticed was that nothing happened. So Einstein's conclusion was that, okay, this is the important factor in determining whether the photoelectric effect will occur. What that means is that the frequency of the photon, or the frequency of light, matters, but the amplitude does not. And so his conclusion was that, okay, well, what if amplitude is actually just a bunch of small waves being added together to make a big wave? And so what he said was, okay, light must exist as a photon. Because if each of these works, then that one should work. But if each of them doesn't work by itself, low frequency and low amplitude, this is still not going to work because each individual photon is what's responsible for causing the photoelectric effect to occur. In other words, if this is my atom here, here's my electron, here comes my photon of light, it's either going to escape or it's just going to go back around to where it was. And even if it's over here, like in the process of escaping, the odds of me getting a second photon to hit it at that moment are essentially 0. So I can only ever really use one photon at a time to interact with my electron. At least that's what he proposed. It turns out that's pretty accurate. So either our photon has enough energy to cause my electron to go whee and break the attraction from the nucleus, or it just raises it up and then it goes back down into whatever it was doing. So the photoelectric effect was a really convincing argument for the presence of photons. And if a photon carries the energy, then that energy is related to its frequency, and the formula for that can be calculated. And here that is. The energy of a photon is equal to some constant times its frequency. Now remember that the speed of light is equal to lambda times nu. I wrote nu first for some reason. And if I solve for nu, that gives me this. So if I have the wavelength, I can just substitute out the frequency for the wavelength. What is h? H is a constant. H is known as Planck's constant. And it is the tiniest number you will ever see. 6.626 times 10 to the minus 34 joules. A joule is the unit of energy, times seconds. The units are just there to cancel the stuff out that we don't want, such that the answer gives us the units that we do want. Energy is measured in joules. Frequency is measured in per second. I want this second to cancel out with the per second on my frequency. Now, depending on what happens with our electron that we are observing and the system itself, we're going to assign it a term. We're going to either call it exothermic because the energy is leaving the system, or endothermic because the energy is being absorbed by the system. So here I'm going to use this red box. This is my system. The system is going to be the boxed portion of the metal that is hit by the photon. When the photon goes in and the metal absorbs the photon, that process would be endothermic. The energy is going in. The system has it. Now, I can transform that energy into kinetic energy, which is what the electron now has when it's ejected. This would be exothermic. Remember, this is all within regards to the system. If I throw a ball, I have to provide the energy. I lose the energy and the ball gains the energy. In theory, if I threw enough baseballs, I would get tired and I would need more energy, right? The same thing is happening here. I am spending the energy that I gained from the endothermic process to throw the electron and eject it. That process is exothermic. So these two terms we're going to refer to quite a bit. Endo means energy goes in. Exo means energy goes out. All right. Let's do an example to try and calculate how much energy a photon has, just for practice. So how much energy do I need to provide atoms in order to get them to do the photoelectric effect? So let's look at this photon. A photon of light from a red laser has a wavelength of 635 nanometers. What is its energy per photon? All right, so let's write down the formula for energy. Energy for a photon is h times nu, or hc over lambda. Hey, we have lambda, so we're going to use that version of it. And Planck's constant is this number. This should be a minus, sorry. That looks kind of sketchy there. So I'm going to just plug in all the numbers. I know what the speed of light is. I guess we'll write that down. So we'll get Planck's constant here. Times the speed of light. And right away you'll see that this unit cancels out with that unit. Divided by the wavelength, which is 635 nanometers. So 635 nanometers is the same as 635 times 10 to the minus 9 meters. All that metric to metric stuff that we were doing at the start helps us save some time here when we get to this part. Now the meters cancel out with this meters, and the unit I'm left with is the joule, which is the unit of energy. So let's punch it in. 6.626 times 10 to the minus 34 times 3 times 10 to the 8 divided by 635 times 10 to the minus 9. I should get something 10 to the minus 19. 3.13, yeah. Ten to the minus 19 is very common for photons. So what this means is that an individual atom needs very, very little energy, because the photons don't have that much energy on their own. A single photon has a very small amount of energy. Now, for comparison here, just in case you haven't taken a physics class or you forget, let me see here. 1/2 m v squared. I want this to be 2. Okay. If I had this 2 kilogram object moving at 1 meter per second, this is the formula for kinetic energy. Oops. I forgot my 2. These cancel out, and I get 1 kilogram meter squared per second squared. This is a joule. So this unit right here, this weird unit, that's what a joule is. That doesn't really make too much sense conceptually. Like, why is there a square area mass per time squared? Like, huh? This is just how we've defined energy. And so 1 joule would be a 2 kilogram block moving 1 meter per second. That's not very fast, right? 1 meter per second. And 2 kilograms is not a lot. That would be Maya. Maya weighs a little more than 2 kilograms, though. So if my cat bonked into you at a speed of about 1 meter per second, the force that she would impact upon you is 1 joule. We're working with 10 to the minus 19 joules. So this is like the teeniest amount of energy that you could even conceive. Now, depending on the material, you need to either increase energy or decrease energy to create the photoelectric effect. And that will require you to tinker with the frequency, which also affects the wavelength. So in these practical problems here, what I want you to do is figure out... I'm looking at the third question, and it's not making sense to me. Oh, I see. Okay, it's this laser up at the top. Okay, never mind. So I want you to answer these questions. So first of all, this is a conceptual question. What color of light has the highest energy and what color of light has the lowest energy? You should probably know that off the top of your head, but can you prove it using numbers? Well, sure. You can go look up the wavelengths of different colors of light and try that. For this second question, I give you a laser with this frequency, and we test it for the photoelectric effect. And we find out that no, the photoelectric effect does not occur with this laser. So, which of the following conditions down here could potentially make the photoelectric effect occur? And then once you've done that, calculate the energy of the photon that I've highlighted in yellow for the top problem here. So, for this question right here, tell me the energy of this photon. Okay, I'm going to give you about 6 minutes to go over these on your own. We'll go over the answers together. Most of these are conceptual. There's only one calculation on here, so keep that in mind. Type in your answers in the chat when you are ready. So if you increase the intensity in which way? So are you increasing the intensity per photon, or are you increasing the intensity by firing more photons? Because one of those will work, but the other one won't. Remember how the photoelectric effect was shown to occur? Which feature of a photon triggers it? We'll go over the answers in about 2 minutes. All right, let's go over the answers here. I need to call this up here. That's the wrong window. That's the right window. There we go. So let's show which photons have the lowest energy and highest energy mathematically. So here are some wavelengths for light. We're not even going to do the math here. What we're going to do is we're going to write down the formula for energy of a photon. So there's a formula. We're going to use this formula because we know the wavelength. If I put a larger number here, then the E I get is smaller, right? Because I'm dividing by a bigger number. If I put a smaller number here, then the number I get for E is larger. So based on that, this is a larger number, so I should have a lower energy for red than I do for purple. And that checks out because we know about ultraviolet and infrared, right? Red is the lowest energy color, and purple is the highest. So we didn't even need to do a calculation. We just had to look at the formula there. All right. For the next one, we don't get the photoelectric effect for this frequency. So the frequency was 4.0 times 10 to the 14 hertz. We don't get the photoelectric effect. And we said that before, the thing that induces the photoelectric effect is frequency. So we need to make the frequency bigger. That's the only way that we can make the photoelectric effect occur. So if we use multiple lasers, so if this frequency doesn't work, it doesn't matter how many lasers we fire with the same frequency. None of them are going to work, and all of them together still does not work. So you cannot induce the photoelectric effect with a higher amplitude. You need each individual photon to carry enough energy to do it. So that means we have to tinker with the photon. Well, if I want to increase frequency, what happens to the wavelength? Well, here's the formula for wavelength and frequency. If this number goes up, because this is a constant, this number has to come down. So the laser that I want that would have a higher energy would have a lower wavelength. So a lower wavelength will lead to a higher frequency and will cause the photoelectric effect to occur. So that's the answer to the second question. And then for the third question, how much energy does this photon have? Well, we'll just enter the equation here. So there's Planck's constant times the frequency. Seconds will cancel out with per second. And the amount of energy that I will have will just be in joules. And it should be a small number. $2.7 times 10 to the minus 19. There you go. So we can use the formula, but coming up in the next few sections, we're going to do one more calculation. After that, it's going to be all concepts. In fact, after this next section, section 3.2 that we're going to do right now, you're going to put your calculator away and never touch it. You will not use it for the remainder of this class. And by class, I mean the rest of the quarter. Believe it or not. That's not like you can't use it. It's just you won't need to. So let's address all of these crazy bullshit ideas and put them all together. So what we discussed earlier was that we got line spectra for particular wavelengths if we looked at a specific element by itself. And those spectra correspond to specific frequencies and wavelengths, these four right here. We also talked about how energy can be quantized in waves and that light exhibits wave-like properties. Could these two things be connected? The answer to that, of course, is no. There's nothing that we care about in this chapter. Let's just go to chapter 4. No, of course not, right? Of course they're connected. So how are they connected? That's the thing. And the person who discovered this was named Niels Bohr. Niels Bohr had this idea. He said, okay, what in my atom is going to absorb light? So here comes my light. What will absorb it? And he decided that the most likely candidate, based on what was known, had to be the electrons going around the outside. Now, if you have a high enough frequency, then the electron will just go whee, and it's gone forever, and this would be the photoelectric effect. But if you don't induce that, and you use a lower energy photon, then what could happen is the following. Well, if light behaves like a wave and electrons behave like waves, then maybe this could be happening. We're going to draw a really zoomed in version of our atom. So here's the nucleus. And here's my electron going around the atom. I'm going to call the energy level that it is sitting at, whatever its energy is, I'm going to call that just 1. Because we're going to treat it just like the waves from before, where we had the standing wave for n equals 1, and then I had the wave with a node in it for n equals 2. It had 2 humps, and then there was 3, and so on. And so let's just number a bunch of these. Now, if electrons are behaving like waves, what that means is we could give them enough energy and change their wave. But the amount of energy that we give them is strictly correlated to these energy levels. Just like with the rope example, if I want to continue to have a wave, I have to put in a very specific amount of energy. And so Niels Bohr said, okay, I'm going to bombard this with my light. There's my light. And my electron's going to absorb it, and it's going to go somewhere. Whee, here it is now. I have absorbed the light. That is endothermic. Now, at some point, the electron is going to absorb, or not absorb, release the light so that it can relax back to how it was. And so when it does that, it will change from whatever state it's currently in to some other state. That could be this state, or it could be this state. The difference in energy between those states must correspond to the wavelength of light that comes out. And if we see the same photon every time, because remember that this is going to be corresponding to some wavelength, if I see the same color every time, that means that these numbers are fixed. And thus, every time I do this experiment, I will get the same result. And that was what Niels Bohr theorized. He said, okay, here's my idea. Electrons absorb light. They go up to a higher energy level because that's a different waveform. And then eventually they relax. There are only so many possibilities because you can only make waves so many different ways. Those possibilities correlate to the colors we see. I told you quantum mechanics was crazy. This is that part. And we're only getting started. So there's the theory in words here. Electrons live at certain energy levels. We're going to call those potentials. And when you give energy to an atom, the electrons absorb the energy and they jump up. They become a new wave. They go to the next level. Now, they could go up one level or they could go up 70 levels. It doesn't matter. But when the electrons fall back down, every time they fall down, they release a photon. And that photon is going to correspond to where the electron was and where it ends up. And if there are only so many transitions that occur, I'm only going to see so many colors. So let's look at that. Here's a picture of that I tried to draw. It turns out that the distance between specific energy levels and the second level, not the first, but the second, fall into the spectrum of the visible range. If an electron that started at 1 moves up to 3 and then falls down to 2, this energy difference is just right to fall in the red region that we can see. And if it goes up to 4 and falls to 2, that's light blue or cyan. And if it goes from 5 to 2, that corresponds to violet. Are these energy levels different than the different rings they're on? Here's the fun part. Electrons don't live on rings. These are the three-dimensional spaces in which electrons live. Because remember how we did this in 2 dimensions and we saw all these nodes and stuff? These aren't the nodes. These are just lines representing how much energy there is. So this is not distance from the nucleus. This is increasing energy. However, later on we're going to learn that energy correlates to distance in some way. So this diagram actually is not showing a radius. It is showing how much energy these electrons have. It takes little energy to get my electron to be on n equals 1. It takes a lot more to get it on n equals 2, and then more than that on n equals 3, and so on and so forth. What's the equation that tells us how to calculate the difference between these energy levels and how much energy you get from that transition? That equation is called the Rydberg equation. We'll show that on the next slide here. Where is it? There it is, right here. So what this equation says, we'll go back to the previous slides in a second here. What this equation says is that the inverse of the wavelength that you observe with your eyes corresponds to some constant times the difference, or the inverse difference squared, of the energy levels that you start at and end at. Yes, this is an obnoxious equation, and they solved this by basically guessing and testing. Now, in order for this term to be a positive number, this number right here has to be the final, and this number right here has to be the initial. Wait a second, hold on. That might be backwards. I'm trying to do this in my head here. I want the bigger number to be here. Let me define this really quickly first, because I'm doing this in my head and I'm confusing myself. So, okay, so this is the initial and this is the final. So, if I have an electron that moves down to emit light, then this must be the initial and this must be the final. Because otherwise you get a negative number, and that doesn't make any sense. You can't have a negative wavelength. So let's really quickly do an example, and then, well, I guess, actually, let's go back and just do this really quickly. And then we'll do an example, and you'll see how the Rydberg equation works. The Rydberg equation is actually really simple in theory, but doing all the math is obnoxious. So when we observe these transitions, which we showed here, our electrons can only land on these energy spaces, because if they don't have the correct energy, they won't form waves. So what that means is that for our conceptual example here, electrons only land, in air quotes here, on these levels n. They are never between. And so that means that we are only ever going to see, so this would be 4 to 2. This would be 5 to 2. We're never going to see something like 2.5 to 2, which would be right here. That's why this is blank. Now, for different elements, there are different levels. All the levels move. And so you get different colors. Excuse me. We're going to talk about why the orbitals, which are the waves that the electrons form, move around as you change the contents of the nucleus. Because helium is different. There are 2 electrons, but there are also 2 protons. What does that do? It does all sorts of crazy shit. We're going to just work with hydrogen for these examples here. Now, let's go back to this diagram right here real quick. And let's suppose that instead of going from 5 to 2, I went from 5 to 1. Would 5 to 1 be larger in energy or smaller in energy than 5 to 2? Well, it fell further, so this is a larger energy photon. But what's larger than purple? Well, that photon you couldn't see, but it does exist. It's in the UV region. What if instead of falling from 5 to 1, I instead fell from like 5 to 4? That's a tiny drop. Where would that fall? That would fall over here. Now, this diagram is a little bit exaggerated. In reality, what our diagram is going to look like is something like this. And we can conceptualize this with that demo of the professor trying to make the standing waves. He had to put in a lot more energy to get the second one, but then to get the third or the fourth or whatever past that, it was really fine control. And that's because the energy required to do these wave functions starts to get closer and closer and closer and closer and closer together. Until you just get a mess, which is infinite. You have an infinite wave. And so you can see here that if everything going down to 2 gives us visible colors, going to 3, this would be our IR transitions. And then going to 1, those would be our UV transitions, because these are much higher in energy than these were over here, which are lower in energy. So depending on where you start and where you end up, you are going to have a different result. And that result, using the Rydberg equation right here, will correspond to a wavelength. We're going to talk about the principal quantum number later. For now, just know that these numbers are, we're numbering them. Wave 1, wave 2, wave 3, wave 4, etc. So let's do an example. We'll do one example before we go, because we're going to run out of time. And so I want to do the wave for 3 to 2. And let me get the Rydberg equation up there, or the Rydberg constant, because I forget it. That's not Photoshop. There we go. All right, so let's write down the equation. So 1 over lambda is Rydberg constant times 1... Oops. I was looking at the wrong screen. So we'll go final minus initial squared. And I want to figure out what this difference is here. Because we said this should be a photon that we observe. And we're going to figure out its wavelength. And then we'll look at this visible spectrum and see where it occurs. So we've got the Rydberg constant, which is this. Oops, I forgot my times 10 to the 7. Per meter. The per meter is strictly here so that I get per meter here. And then I'm going to take the inverse later on to get the wave, or the wavelength. 1 over n final squared. So this would be my n final, this would be my n initial. So this would be 1 over 2 squared minus 1 over 3 squared. These are integers, so they are exact. We are counting levels here. So this would be the Rydberg constant times 1 over 4 minus 1 over 9. And when I punch all that into the calculator, I get 1 over lambda equals times 1 over 4 minus 1 over 9. I get 1523300. Now there's a lot of sig figs here because this is well known. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. There we go. That's not a wavelength, though. That's an inverse wavelength. So now what I got to do is I got to take this and invert it. And so if I take the inverse, that's going to be equal to 1 over this number, which equals 1, 2, 3, 4, 5, 6, 7 times 10 to the minus 7 meters. I forgot my meters to the minus 1 here. Which, if I do this, becomes this number. Which becomes this number. Look at that. Guess what color that is. Remember what color red is? Red is around 700. That transition is the red line that you see on the hydrogen spectrum, which we'll put right here. There it is. So you can do that calculation for any two energy levels. And I would encourage you to do that because there is one of these on exam number 1. Okay? So work with the Rydberg equation over the weekend. All you have to do is plug in the numbers. And then cover the concepts that we've studied so far in Chapter 3, the broader concepts, so like photoelectric effect, waves, nodes, etc. And that should be good for the Chapter 3 content that's on exam number 1. There's not that much of Chapter 3 on exam number 1, because obviously we only spent about 3 hours on it. But there is some content there. Alright, so I'm going to go back to here. We're going to just put this here where we were. And that's it. That's all the time that I have. I think I actually went over. Yeah, it's 7:01. So, alright, so I sent out an announcement, I believe yesterday, that says the exam number 1, is on Monday, February 8th. Okay? What that means is that on Monday, I will open the exam, and it'll be open for 24 hours. You have to take the exam on Monday. If you try to take it early, it will say it's closed, and if you try and take it after the deadline, it won't let you. Okay? You have to take the exam on Monday. Okay? I realize that's different than what's in the syllabus. I did have to move it due to some issues that I had, so I apologize for that. If you absolutely can't take the exam on Monday for some reason, say you have work, or you have another class that has an exam on Monday, or something, let me know, send me an email. I will specifically move the exam for just you forward or backward one day. So you could take it on Sunday, or you could take it on Tuesday. I would prefer that you take it on Monday, because otherwise I got to start setting up exceptions. But if you absolutely can't, for some reason, let me know and I can work with you, okay? Quiz number 3 won't be open because we're nowhere near done with Chapter 3. Quiz number 6, however, I have set the deadline to be Friday. That means that's the soft deadline. The hard deadline is Saturday. I will open Quiz 6 on Sunday so that you can study from it. And then the exam will be Monday. And the exam on Monday will be chapters 1, 2, 6, and everything we've done of 3 so far. Alright, if there aren't any questions, let me know in either Discord or email. I will be available all weekend for you to answer questions. The only exception is Monday. I can't answer any questions on Monday while people are taking the test, okay? Yeah, that's really all I got. So, best of luck studying this weekend. Make sure to get the assignments done in for Lab 2 and Quiz number 2. And good luck. We're all counting on you.